My name is Oded. I'm a solution engineer at VMware Tanzu, where we basically work with the customers on everything related to Spring, to Kubernetes, Cloud Foundry, RabbitMQ, all of this fun stuff. And today I want to talk to you about how to run Spring in Kubernetes and what considerations you should take when you do such a thing. In VMware Tanzu, we have an annual survey that we do with our customers where we basically check what is the current status of Spring on Kubernetes. And in the most recent one, we found that we have a spike from around 44% to 57% of users already running Spring in production on Kubernetes. And as we see, the time goes by, this number just keeps growing, and Kubernetes really is becoming the de facto standard in our industry. So what considerations should we take when we are running such workloads in Kubernetes? And there are really two aspects to it. The first one is how to build the image, and the second one is how to run the image. So let's take each one of them separately and have the assumptions and considerations that we see fit. So with regards to building the image itself, some of like TLDR, just very basic stuff, and then we'll drill down even deeper. It is still recommended to use Ubuntu or Debian or PhotonOS or Red Hat Enterprise Linux, whatever it may be that uses the glibc kernel. Only since JDK 16 and later, we now support the Muscle library, which is a much more lightweight. Things like Alpine use that. So I would say it's still early days for that, but definitely something to keep in mind for the future. So I would say stick to glibc for the time being. In terms of the JDK distribution, there are a ton of vendors out there, things like Bellsoft and Azul. Obviously, Oracle is one of the main options. So anything that really supports the what is now called the Adoptium distribution, what used to be called the Adapt Open JDK, which is basically a community-driven effort for OpenJDK, is going to be a great option, like the Eclipse Tamarin 17 based on Ubuntu Jammy that we see here. And lastly, kind of obvious, especially with the announcement today of Spring Framework 6 and Spring Boot 3, it is highly recommended to use the latest long-term support version that you can. Currently, this is Java 17, and we'll have 21 fairly soon. And we should really get into this mindset of updating our Java much more recently than we might have done in the past. Now, just to have some sort of indication on that, so this is not just for features like Jürgen said in the morning. Here's a Java 11 application, the famous Spring Pet Clinic application. And the boot time for this, based on JDK 11, is around 9 seconds, right? Now, just by upgrading my JDK, not changing the Spring Framework version, not changing anything at all, just by going to version 17, I'm already 1.5 seconds faster at my boot time, right? It's 7.5 seconds in this case. So every time there's a new release, there are improvements to the underlying infrastructure, and it's definitely something we should take into consideration. Now, how many of you are still stuck on this? Java 8. Oh my goodness. I'm so sorry for you. You're not alone, as you can see. I think like 30% of the people here are still on Java 8. And actually, you're not alone. In a recent survey by JRebel, around 37% of respondents say that they are still bound to Java 8, and it's quite hard for them to upgrade to a more recent version. So definitely we want to think, how do we run these more legacy Java versions on Kubernetes? And the number one thing that you need to take into consideration if you're still running Java 8 is that only since update 121 and later, the JVM is actually container aware. Okay, this means that everything related to setting the garbage collection, the heap memory, the thread pool sizes, all of these things use the argument of get available processes that the JVM uses to make a lot of assumptions. So before 191, it actually used the host's CPU and memory, which means that it got basically the wrong information, which could obviously cause a lot of havoc if you're going to use it in a production environment. So just as an example, here I am running Java 8 update 131, and I'm requesting 256 megabytes of memory and 2 cores from my container. And basically, the JVM tells me, I don't care what you told me, I'm going to give you 4 gigabytes and 4 CPUs of runtime. So obviously, this can be a big problem for me going into production. using the same application, but using a more later 292 version of Java 8, I'm actually getting the correct value of around 132 megabytes and no parallel threads in this example. So make sure you're always on, if you're on Java 8, as I see many of you are, always use the latest patch version. It's not just for this specific use case. Even the latest patch versions that are still being released in the OpenJDK community are having additional benefits while running in containerized environments. For example, this new feature request in the JDK community is enhancing the container awareness to use cgroups version 2, which is basically the more common Docker engine that we're using in the wild today. Up until today, it is still using the older version. And in Java 8, in fact, it is still using version 1. It is still in active development at the time of this talk. So every time you can, upgrade to the latest patch version, or you're going to get quite problematic performance in the future. So let's talk about writing Docker files. How many Docker files look like this from people in the room? I saw many of you use Docker files. OK, 1, 2, 3. OK, that's good. So this is actually from, unfortunately, still available online from Spring.io as one of the examples. Basically, take a base image, add the target jar file, and run it. Do a Java -jar, right? And this would work. This would actually boot up, and it will work, and everything is OK. But it is not exactly optimized, right? And the reason it's not optimized is that we're basically taking this 150, 200 megabyte jar file, this Uber jar that Spring Boot creates for us, and we're putting it in its own layer inside the Docker container, right? Now, what does that mean in practice? In practice, like Deshaun mentioned earlier, when you're building the image, every new build creates another 200 megabytes layer. And that 200 megabytes has to be pushed to the Docker registry. And later on, from your Kubernetes cluster, you have to pull 200 megabytes to your node. Now, do you really need 200 megabytes? What did you change, really, in your application? Maybe the top 10 kilobytes of source code that you changed between builds, right? So we really want a more optimized experience here. Luckily, Spring has a mode to actually give us that option. So if you run Java on a Spring Boot application and you give it the jar mode equals layer tools, you can provide all kinds of parameters for it. Things like list the layers that you think are optimized for a production environment, for a Docker container. So here we're seeing that the recommendations are create a dependencies layer, create a Spring Boot loader layer, create a snapshot dependencies layer if you have any snapshots in your application, and only then create a layer with your actual, custom code. Luckily, Spring even lets us use the same tool with the extract command, so we can actually unzip the Uber jar into separate folders, and each folder represents its own optimized layer now, right? So using this behavior, for example, here we have the dependencies folder, and we have the application folder. So the dependencies basically contains all of these probably 100 plus dependencies we get from the Spring ecosystem. And our application layer only has just a couple of kilobytes of source code that we wrote ourselves, right? So using this mechanism, we can now write a much more optimized Docker file where we basically do a multi-stage build. We start by compiling the application, and then we extract it to multiple folders, and then in a separate stage, we create a separate layer for each one of these folders, right? And now you basically have the optimized Docker file. Now, this also has, again, performance benefits. So the same application started up 6 seconds when we used the Uber fetch jar as before. And if we use a Docker container that was built with the layer tools, we're actually down to 5.5. So additional 1.5 seconds of startup time improvement just by using an optimized Docker container. So avoid using these fetch jars in Docker files and use the layer tools for correct layering. Now let's talk a bit about JVM configuration. As you know, our JVM consists of heap memory and non-heap memory. The heap memory is basically where all of our various code is managing the garbage collection, the classes, the objects that we move around. And the non-heap memory is used by technology such as NeoIO or Kafka or databases which basically gives you direct access to be outside of the heap itself. And your JVM uses both of these parameters, and you have to make sure that the total of these two parameters is less than the total available memory in your container. Otherwise, you're just going to get an out-of-memory error as you would otherwise, right? So by default, if you don't change anything, if you just let the JVM do its thing, it's going to set the heap memory to 25% of available memory most of the time, right? And the non-heap memory, we really don't really know how much we're going to use at runtime. We have to profile our application in order to get that information out of our application. So we can use the setting when we run our JVM. We can ask for native memory tracking. And for example, here we just profile it. We run it in some testing environment, let it run a while. And once we stop it, we're going to get a report. This is the amount of native non-heap memory that our application actually consumes. Okay? So it is highly recommended to avoid the defaults because these defaults have a lot of impacts on how your application is going to behave. So you should probably change these memory settings using the Java tool options environment variable in order to make sure that it fits the environment. Now, what parameters should you give is kind of its own question here. It can be kind of problematic to notice. Luckily, at Pivotal, we created this very nice tool called the Java Memory Calculator, which basically, it's a simple script in the end that takes this guesswork out of the picture and has a very advanced algorithm based on use of production experience. And we can use it in order to determine what is the recommended starting point for our application. So for example, here, I provide to the binary the things that I know, and it's going to output the things that it recommends as a result. So here I'm asking, my application has 750 classes, around 100 threads, and around 1 megabyte of stack size. And it says, well, your recommended heap size in that scenario should be 670 megabytes. Now, here's an interesting point. If I'm profiling my application and I understand, actually, my application uses 300 threads, right? Suddenly, each thread obviously consumes more from the heap. So now my recommended heap size is down to 470 megabytes. And as you can see here, it always gives me some default 10 megabytes value for the direct memory size, because it really has no way to know how much native memory I'm going to consume. So if I profile my application and I realize I need much more, then I can provide it as input, and now my recommended heap size is down to around 400 megabytes. Maybe it's time to increase the available container memory from 1 gigabyte to something larger. So profile your applications and try to avoid the JVM defaults because they can have a lot of impact on your application, and use explicit memory arguments with the Java memory calculator. Now, as Deshaun mentioned before, who needs Docker files? It's 2022. I mean, come on. We can definitely forget all about this headache, and I highly recommend that if there's something that all of you are taking from this day, is that you can basically replace your Docker file with build packs and have a much better experience. So Docker or OCI images, as they are properly called, are great. They're immutable. They can run anywhere. But the Docker files themselves have some obviously good things. It's very easy to get started, and you control the entire stack of the final image that you're creating. But it also means that you control the entire stack that you're creating, right? So you're basically in charge of the CVE patching, you're in charge of the technical debt, and the standards are set by people and not platforms, so this can obviously become a very big technical debt for an organization. Now, there are tools like Jib. Google uses that. It's very popular. It creates an image from a Java application. But I definitely recommend going with build packs, or cloud native build packs as they're called, because they are a standard in a community. They've been around for years. We have millions of applications from the Cloud Foundry world and Kubernetes world using it. And it has the benefit of proactive CVE patching, which is very, very important. So every time you rebuild your image using build packs, you're going to get the latest builder and stack from the community, Paketo or VMware if you use an enterprise version called Tanzu Build Service. And with that, you basically always get the latest patches for the operating system and the JDK. So the TLDR is just run Maven Spring Boot build image and be done with it, and you have a production-ready image that's ready to go. It's going to layer it exactly like I mentioned before to make sure it has the proper layering. And it's actually going to run the Java memory calculator for you on startup, right? So here, if I have a lot of CPU and a lot of memory, it's going to set the active processor count to 4, and it's going to give me 32 gigabytes of available memory, which is kind of crazy because this is a VM that I have. But if I run it in a constrained environment, it's going to use different parameters. So here it set it to 1, and it gave me much less available memory. So it's environment specific. Whenever I boot my container, I get the correct parameters for that environment. All right, so we talk about building the image. Let's mention some of the aspects of running the image in Kubernetes itself. So the first thing we need to think about is our application alive and can it respond to client requests, right? We're all building Spring applications. We're all using the 12-factor app, trying to use the 12-factor apps model in order to make sure that our application is cloud native. But one of the most important aspects when you run an application in Kubernetes is answer this question. Can you restart it gracefully and be sure that it will come back online without any issues, right? That's basically the number one thing that you can do to make sure your application is production ready, because then Kubernetes can take care of a lot of things for you without having to make any changes to the code itself. Luckily, we have the actuator endpoint, which gives us a lot of information that we can use to make sure our application is alive and ready to serve workloads. And we can just add it to our dependencies, and we're good to go. So this could be like a sample part of the deployment YAML. We basically point our liveness probe and our readiness probes to actuator/health, and we're good to go. We basically say whenever there's a problem, it will restart. If it returns to 100 OK, we're ready to go, and we can serve traffic. But now, again, there are considerations. So the first one you should think about is, should you really restart your application whenever there's an error at an actuator endpoint? Right? Think about it. The actuator is checking the health of the entire application. It checks if the database is responding, if the RabbitMQ is working, if a third party that you implemented is responding correctly. Maybe if it's down for a couple of seconds, you don't want to restart. Maybe if you restart, you're going to create even more problems in production because you keep creating more and more connection pools. And it's a cascading failure in the end, right? So you have to understand what kind of endpoints should you check, what kind of third parties should you check when you're polling this endpoint. Also, you're usually expected to run the actuator endpoint on a separate port from your application because it can expose a lot of metrics and a lot of sensitive data about your application, which could be a security problem. However, you do want your liveliness and readiness probes to be on the main application thread. It doesn't help me if I'm probing and I get a 200 OK from the management port. That doesn't mean anything about my web application. I want to poll the 8080 port and make sure that it works as expected. So luckily, Spring has us covered here, starting with 2.3 and later. We have the option to use health probes. We basically have this parameter enabled, set to true, and it is the default value if you're running in Kubernetes. Spring identifies when it runs in Kubernetes, and it sets this value automatically. And now we have two additional endpoints. We have the /readiness and the /liveness, and these are basically the ones we should poll, and they don't do by default any external state checks due to what we said before. We're basically making sure that, are you up? Good, let's go. We'll take care of the rest later on. You can customize it like I'm doing here. You can override the defaults and say, I do want to probe my database or my endpoint, third-party endpoint, but I don't want to poll for Redis cache because who cares if it works? You know, worst case, I'll go to the database and let my application run. Now, starting in 2.6 and later, we also have the ability to overload an additional endpoint that exists in a separate port on the main application port, right? So here we're basically saying we want another path for the readiness probe, which runs on the separate management 9090 port. We want another endpoint for it, another path for it on the main application port. And we basically say here /readyz on the main server 8080 port in this case will return the same information. And now we can basically configure our application like this, and we say we're going to pull the actual application port, make sure that it works, and everything works exactly as expected. So there are other parameters here, obviously, that you can configure. The period seconds is basically how often to poll for this endpoint. The timeout seconds, if there is no response, when should you time out? The initial delay seconds is telling you how often should you wait when you start up the application, when you're just running live. How often should you wait before you actually get a value? So when you have a readiness probe, you want to wait for the application to start before you keep asking it, are you ready, are you ready, are you ready, right? And you might want to have a threshold for the failure, so you don't just immediately restart. Maybe it's a temporary network hiccup or something like that. So use the built-in readiness and liveness probes, and keep the probes on the main application port, otherwise you're getting false positives, and everything else should remain on the management port, things like metrics, etc. Now let's discuss graceful shutdown. So when our application gets a SIG term, basically, when you get a message from Kubernetes that it's time for us to stop the application, by default, in Spring, even today, it immediately stops the application. We're done with it, we're exiting. And all in-flight requests will be terminated, which is obviously not what we want to do when we run in a production environment. So with version 2.3 and later, we have this setting, server.shutdown equals graceful. What this is going to do is basically it's going to stop the world. It's going to prevent the JVM from being terminated for a predefined period of time to let all the in-flight requests finish processing, and then we can really shut down as expected. How much time should I wait? It's application specific. You can define it using the timeout per shutdown phase. By default, it's 30 seconds. Here I changed it to 20, right? So just give it some time to finish all the in-flight requests before you are done with your termination phase. Now, you might want to do it only when you run in Kubernetes, so you can do it with profiles. So here we activate these settings only when we use Kubernetes. There's a specific configuration called activate on cloud platform, and these settings below will only be relevant when I'm running in Kubernetes. Now, that's not enough, unfortunately, because Kubernetes is a distributed system. We have many moving parts, lots of pods and load balancers and API server and whatever it may be behind the scenes. And we have to take some time before we shut down our application to make sure that all of these various components are in sync. We say, OK, I'm not going to send any new requests to this application. Otherwise, what's the point of just waiting for it to shut down? So here we basically can have a pre-stop phase, where we basically say, before you really kill the application, sleep for 10 seconds, and only then start the termination phase. And there's also another setting saying termination grace period seconds, where it says, OK, if I sent a SIG term to the application and nothing is responded, after 30 seconds, just kill it because I can't wait any longer. It's too much. Now, here's an interesting point. We have basically an interesting flow here, where we have the pre-stop, right? We're waiting for 10 seconds. Only then Kubernetes sends the SIG term to our pod. Our pod begins the shutdown process, right? And for graceful shutdown, it counts the shutdown phase period, okay? And beyond all that, you also have this separate termination period seconds value that we have to think about. So the formula here is basically make sure the termination is larger than the pre-stop and the timeout phase, okay? Otherwise, you're going to be in a world of hurt because all your pods will be killed abruptly, right? And the bad news is that the default for the termination phase is 30 seconds, and the default for the shutdown phase is also 30 seconds. So congratulations, you will always kill your pods violently instead of gracefully, right? So make sure that you are setting the values correctly in order to have the correct shutdown process for your Spring applications. All right, last two items, CPU requests and limits. So, as we said, there are a lot of assumptions being taken by the JVM based on the number of available processors in our application. In Kubernetes, 1,000 millicores equals 1 vCPU. And this is basically the minimum guaranteed amount that we're going to have, right? This CPU request is related to resource allocation. It has nothing to do really with performance. CPU limits, on the other hand, allows you to start throttling your application if you consume too much CPU. So it can impact performance. What should be the values for these two parameters? And the general answer, due to time constraint, we won't go deep into each one of them. Always set CPU requests, never set CPU limits, okay? What is the point of you setting CPU limits, honestly? Maybe it makes sense if you are running it in some profiling or performance testing environment, and you want to make sure what is the correct defaults for production. Once you go to production and you have available capacity, let it use the capacity. Don't constrain it artificially for no reason, right? So that's probably the best setting. Again, this is not just me. This is like Tim Hawkins is one of the founders of Kubernetes. This is one of his recommendations. Never set CPU limits. Otherwise, you're going to get into, basically, you're going to block your application for no reason, really. So here's a sample. You basically set the request, and you don't touch the limits at all. Now, bad news, as always, things changing in the Kubernetes and the Java ecosystem. And now there's a new feature request, or even a bug to be exact, in the OpenJDK community, where we basically say do not use the requests parameter to define the active processor count. What? We just said this is going to be a problem. Why do we want to do that? And the reason for that is that the CPU request is the guaranteed value, right? As we said, we don't limit it. We just say what is the minimum amount you can get. Let's look at an example here. So let's say we have a node with 16 cores, and I'm requesting a container of a Spig Pen Clinic, and I'm giving it 4 cores of CPU, right? What is the value I'm going to get? How many cores my application is going to get in this scenario? Any ideas? 16. Perfect. There's nothing else on the node. Take whatever you need. That's the whole point, right? So now the active processor count is actually 16. Now another container comes along. I want another 4 cores, right? Suddenly, each container now has active processor count of 8, right? And another one comes along, and it requests 2, and now each one has a separate value which changes completely. So basically what this means is that the value of active processor count will drift over time, and the JVM cannot use this parameter to make any assumptions, which is kind of a pain, right? And if you set it to the default, 1,000 millicores, there's a bug still that will just set it to the host CPU, which is like the worst thing you can imagine. So this can be a bit of a big problem. And in order to fix that, just don't let the JVM do anything by itself. Honestly, don't trust it. Set the active processor count explicitly. You can give it 4, even though the container gives you 2, and that's fine. Allow some bursting, and then you can basically be guaranteed that you don't have any errors. Okay? So set your CPU requests, do not set limits, and set the active processor count explicitly in your application, like the build packs do, by the way. Okay? And the last consideration is memory requests and limit. In this case, the answer is quite obvious. A memory is not what we call a compressed resource, right? So a CPU can be constrained, we can throttle it, but a memory is more like a balloon. If you try that, it's just going to burst, right? So if you basically if the Kubernetes will need to reduce the available memory for your container, this means restarting your pod. There's just no other way for Kubernetes to reduce the amount of memory that you have available. So in order to avoid that, always set the requests and the limits to the exact same value, and then you are guaranteed the value requested, and you will never be terminated if the node is low on memory. Something like this, right? CPU requests and CPU memory, this is a good starting point. So, putting it all together, my colleague Adib Saikali has an excellent tweet on that. Just a good starting point, scale up before scaling out, of course, considering resiliency. Start with something like 2 cores and 2 gigabytes of RAM, explicitly set the active processor count and JVM memory settings, set CPU requests but not limits, and make sure that they are equal. So looking ahead, we saw a lot of items today. We saw Spring Boot 3. Obviously, none of this is relevant for native images. When we go to native images, we have to start thinking about other considerations, right? Project Laden, static images, Project Loom, and virtual threads. These all could have different impacts as we go further, and we have to think about them when that makes more sense. Just as an example, again, I think Deshaun showed it excellently before. So this is my M1 Max build. It took less than 3 minutes for a native image, but the startup time was 0.05 seconds for the same application, right? So that's in all what I wanted to show. If you want to have a deep dive on the actual article. It's like 66 minutes read time if you're really bored. With all of these considerations and much more about Spring Cloud, etc., you're welcome to go to this website or to this short link. And I thank you for your time.